Okay, so hopefully this is coming through loud and clear enough. It's week 13, and I'm just sitting here in my office with Corey and Joe, and what I thought we'd do is go over the quizzes, some of the quiz questions. It looks like there was one problem. Adam, you had emailed me and said that one of the questions was in Jah chapter 4. So what I think I'll do is just not count that towards the grade and then move that problem towards the final and provide you with the information that you need to take that one. So hopefully that's a fair compromise on that question. I apologize for that. I think in the past, most people were buying the book, and then I got a lot of grumbling, like we don't want to buy the book, so I figured I'll copy some of it, but I guess there's a couple more pages I need to copy, so that's fair. Also, I'm just looking at the calendar here, and this today's the 20th. This is week 13. Next week is Thanksgiving week. Basically, it sounds to me like classes are canceled on the 26th, so I'm just going to leave that as a project time for everybody. If you guys need help, Joe, I know you're working on something for the office here. If you want to come in, I'd be happy to take some measurements or consult on fastening. There's still 6 holes where the bolts were. Maybe we want to try to match those up so we're not drilling another. Turn my office into Swiss cheese. Right. So we can measure where those are. Sounds like Corey and Will were working on a project too, and we can talk about that as well. But I thought I'd just go over the quizzes, quiz results now. Do you guys want to go over that now? Does that make sense? A couple questions? Sure. Okay. Mm-hmm. Okay. Once in a while, there's kind of a red herring question in there that throws everybody, including me, for a loop. We'll see if that's the case here. Okay, so quiz 3, attempts 5. So you guys haven't taken quiz 3 yet, though. Okay, no. Let's look at quiz 2 then. So let me just say this to the camera then. Everybody finish quiz 3 before you leave for break next week. Just get that thing out of the way. I'm going to fix the one problem that Adam pointed out that had a question from Jah chapter 4. That question's just going to move to the final. I won't count it against you on quiz 3. So yeah, let's look at quiz 2 then. Looks like everybody's taken it. Nice. And I've got some grades. And those probably aren't final grades. Oh, there goes the basketball. The wig is alive. I think it's okay. Just here, give me that thing.
Wear it.
Yeah. All right. This is something Jonathan Bowe would do, but anyway. All right. Okay, class. Oh, God. Halloween's long gone. Never mind. All right. So I'll just go through all the questions. What the heck? I'm not dwelling. So match the responses with the parts of the collector. So the gross area, as the name implies, is the largest one. It's just how big the thing was. If you were looking at your device from Google Earth, it would be how big the thing looks. The aperture area, that's everything sort of inside the frame material. So that's the second, and then the absorber area is going to be the smallest. Now, it could be that the absorber area is the same as the aperture area, and really that's kind of your goal, is to make it as large as possible. And shoot, there might even be some technologies out there where, I don't know, maybe you got tubes, like maybe the frame itself is collecting energy, and they're all equal to each other. But in general, this is the order. Okay. And then, which of the following is not an advantage of an unglazed collector? So unglazed just means it doesn't have glass on it. And so that's kind of a double negative here, and you got it right. It says it requires less surface area. Now the whole point behind the glazing, the whole point behind putting the glass on there is the greenhouse effect. You know, the all of the wavelengths of light come through that panel, and then once they hit matter, once they hit whatever your collector is, they're going to then re-radiate. But as we know, for glass, the majority of that radiation can't penetrate the glass. It's stuck behind it. It just bounces back and forth and stays inside. So that's the correct way to think about that one. Which of the following is incorrect? Now this is kind of a nasty problem, and it comes out of the solar thermal text, and it's something that I wrote, I wrote all the questions, but it was something that I needed to understand a little bit better. And let's just go over the definition of those symbols really quick. You guys might. You guys might even remember this better than I do at the moment, but you guys remember what page that was on, or where in the book those equations were? I think it was pretty dang early. Yeah. Maybe it's page 23 I'm looking at here. Yeah, it's page 23. So question 3, page 23. And what I and this is the fundamental thing. This is something you got to think about every time you're doing a solar thermal system. Is, you know, the photon comes in, hits your technology, and basically one of three things are going to happen. One, it's going to get reflected, and that's rho. So that's that first equation there, degree of reflection. The other thing that could happen is it just comes in here and gets absorbed, so I'm going to call that number 2, and that's your alpha. And then the third thing that could happen is that it could go straight through, and that's your, so I'm going to call that number 3, and that's tau for transmission. So if you take all of the photons that come in, and we'll just say all of the photons is 1, in whatever units you want to be. You know, it could be 1 quadrillion, 1 10 to the 21st. We don't really care, but the equation is basically 1 equals rho plus alpha plus tau. I mean, that's the fundamental equation. Now, the kind of the curveball here, if you will, is this thing epsilon. And epsilon is this little guy right here. Maybe I'll draw it with a different color. It's not the best color, but it's sneaky, so I'm going to draw it in a little sneaky color. Epsilon is the re-emitted radiation. And I'm trying to draw epsilon as something that leaves the technology. So, you know, inside your technology, you could have something that gets absorbed. That's kind of that mode number 2. It gets absorbed, and yeah, it's gonna re-emit. But what you're hoping is that greenhouse effect is gonna re-emit it and keep it inside your technology. So if we go back to the problem, I mean, those are the four, basically the 4 things. 3 things can happen to the original photon. Then you got to think conservation of energy. It's not going to disappear. I mean, that energy from the photon is going to turn into some molecule or atom or, you know, some substance in your technology that's now vibrating faster. It's become thermal. But that's what you're thinking about here is conservation of energy. So So what I did is I wrote rho, which is the reflection, A alpha absorption, tau for transmission, plus epsilon equals 1. And that's not correct because we know from that last little equation that the emissivity, we know that epsilon equals, I'm just going to write this, emitted over absorbed. And it gets a little. I'm just going to write this as sort of a fourth thing that's going to go on. And obviously, so we know that this equation right here is correct. There can be no doubt about that. But what's basically going on is I don't really like the way this thing is written, because now I'd like to have a variable for emitted, and we've kind of already used epsilon for the ratio. So there's you can see kind of the problem. That's where I was like, why are they writing it this way? So we could rewrite it like this, equals, let's just call it big E for now. And sorry, big E gets overused, but E alpha. So what that would mean would be something like this, where you have 1 equals, well, then if you solve, then that means that alpha equals epsilon E. Then you might try to put that in here, and you say 1 equals rho plus epsilon E plus tau, and then you start thinking, well, shoot, not all of that radiation was re-emitted. Some of it stayed in. So this, so your accounting system kind of breaks down. Anyway, that's not beleaguered. I think you understand the point there. Okay, so the next one. And again, that's confusing because the incorrect answer is, all right. So number 4, which of the following best describes the difference between G and G naught? And then, so what I've got here written is the correct answer is nothing. They both describe the radiation that hits the glazing. Now, I want to dig into this one because it's kind of confusing in the book, and I was confused. That's why I wrote the problem. So what Corey answered, and which is probably fairly reasonable, is G naught is the radiation that hits the glazing, whereas G is the radiation that hits the gross area. And if you can show me that it says that somewhere, I'm happy to give you credit, because it is a confusing problem. But let's just take a look at where that is. Do you mind hitting that light?
25.
Page 25.
Well, 24 and 25.
Yeah. Okay. So what we're looking at is G versus G naught. So Q for G versus G naught. And okay, so the figure 210, and I'll just I'm just going to rewrite figure 210 here. Fig 210 shows big G naught coming in like this, and then it shows little G1 heading off. It shows G2 heading off, and then it shows Q2 heading off this way, and it shows Q1 heading off this way. So it's a much more complex thing than we've been looking at. So I'm just going to read right after. So this is actually in section 2.2.2.2. Nice little number there. It says the irradiance G naught hits the glass cover. Okay, we've shown that here, here, even before it enters a collector, a small portion of the energy, G1, is reflected. Okay, we've drawn that. And that's kind of that, the row part that we just wrote of the pane. The selectively coated surface of the absorber, so that's going to be your paint, your black paint, for example, reflects a small part, G2, and converts the remaining radiation into heat. So with good thermal insulation on the rear and on the sides of the collector, using standard non-combustible, thank you, or non-melting insulating materials such as mineral wool and or CFC free polyurethane, the energy loss through the thermal conduction Q1 are reduced as much as possible. So the Q1 is the stuff that's just leaking away from, well, both conduction through the, so the Q is a conduction and a convection heat loss. I don't think that's the radiation portion. Could be, not that important. The transparent cover on the front of the collector has the task of reducing losses from the absorber surface through the thermal radiation and convection. Yeah, so I guess he's calling Q1 conduction only. He's calling that conduction, and he's calling Q2 convection. And hopefully the directions that these arrows are pointing aren't misleading. I mean, conduction and convection are working hand in hand. I mean, the conduction is what's happening through the technology, and then the convection is what happens at the surface, the heat being taken away. Okay, now getting back to the question is what the heck is, here you can take that down, close it if you want. The question is, what the heck is G? So,
Yeah, that's what threw me is
yeah.
G1 and 2, but it's not just G.
And so I'm looking back through here, as I know that, yeah, okay. If we go to the next page, page 26.
Seems like it should be before you bring G to describe.
I know, and this is one of those things where, I mean, I guess until I write my own textbook, we're kind of stuck with what we got, and we're interpreting it. You know, it's some guy out there who, you know, knows his stuff, knows it well enough to write a book, but nothing's perfect. So I'm just going to look at page 26. And here's the next equation that hopefully draws out G. So it says that eta, we've seen eta before, that's the efficiency of your system. Eta equals Q A dot over G. Okay. Now, we can see and be mindful, there's a little dot there. You guys remember what the dot means? It means the rate. So let me just write this up again for you. So Q equals thermal energy Q dot, guys, tell me what Q dot means.
The rate of energy.
Yeah,
Amount or
thermal power. It's thermal power. Yeah, rate of energy, thermal power. Thermal power, because the dot is just is the rate of change of something, and if you're looking at how quickly that's changing, then that's your thermal power. And then G, what he's got here, G is the irradiance on the pane glass. So G is irradiance.
is that like a measurement of the glass, like how much reflection that the glass has, or what is that exactly?
It's not a measure of the glass. It's a measure of how much radiant power hits the glass. That's all it is. So
and
ra-
from there it goes.
and from there, yeah.
G1 and G2.
Exactly. So it's the same as G naught.
Right.
I mean, and I'm sorry, but I think when I first read it, I was confused, and I don't know. Maybe I'll give you guys another shot at that. And I just felt like you gotta just sit down and
I think I actually got that one right.
good.
But I got that last one wrong.
So it's the irradiance on the pane, and this is measured in watts per square meter, and this is also measured in watts per square meter. And then, gosh, I think it gets down into some other G sub A's and et cetera, but if I were to edit this book, or if I were to send something back, I'm like, guys, don't confuse my students and use G naught and G as two separate things. But I'm just going to read one more time from 2.2. It says the irradiance G naught hits the glass cover, and that's all of it. Yeah, and then on the next page, it says G is the irradiance incident on the glass pane. It's the same thing. So that's the answer.
What was the question?
That's a suck you. It says, which of the following best describes the difference between G and G naught?
It's a trick question.
It's a little bit of a trick question, but the answer is nothing. They both describe the radiation. It's the glazing, and it does say there in the book. G is the irradiance incident on the glass pane, says 126. G naught hits the glass cover. Same dang thing. So hopefully that is clearer, and we can point out to the author now that he needs to revise his book so we're not all confused. But I think you can see why you could screw up pretty badly, lose a few percentage there if you're not paying attention to what you're talking about. Okay. Next one is, according to figure 211, the thermal efficiency of a solar thermal collector that is receiving 600 watts per square meter with a temperature difference of 20 K is approximately, let's go to figure 211, and I'm just going to hold that guy up. So that's what we're looking at here. I don't know if I can get it close enough, but I think what I've done is drawn a little line through it at an efficiency of 60% and an irradiance of 600 watts per square meter. Oh yes, sorry. What I've given though is I've given the 600 watts per square meter. Yeah, so I've given this line, the 600 watts per square meter, and the 20-degree difference, and those intersect right there, and then you draw over, and that's your 60% efficiency. And this figure is just kind of an approximation to it. Obviously, there's no equation that he's plotting, and I'm certain that there are. Remember how we went over Bett's law? I mean, there's no law saying that the maximum. If you look at this thing, you might say, "Oh gosh, why is the maximum efficiency of the solar collector only 80%?" Well, this is just one particular collector. You might have a collector, and it's also an approximation. You might have a collector that's way more efficient than 80%. There's no physical law behind that. Okay. You have designed a solar thermal system and noticed that not all the heat is making into your house. After some measurements, you determine that at a temperature of 20 C, that you are losing about 50 watts on your system, which has an effective area of 4 square meters. What is the heat loss coefficient of your system? I'm gonna see. I hope I have a little. I should have a little solution for that thing here. Let me take a look. I thought I had it on. Where is this? Let's just take one. We're about a half hour. I'm just going to take a quick break. We'll solve it and then come back.